Welcome to Hardfire. I'm Ronald WIECK. We're in the middle of a three-part discussion of the physics of 9/11. Our guest is Ryan MACKEY, a research scientist at the NASA Jet Propulsion Laboratory. We're going to resume where we left off last week, but I want to say a few words about the genesis of these shows. Back in May of 2007, I invited David Ray Griffin to appear on Hardfire to discuss his latest book. Griffin seems to be the man who's most acceptable to all the squabbling factions in the truth movement. His response was favorable. We worked out some sort of arrangement. There was an initial bit of confusion over whether or not he was expected to appear physically in the studio. We finally determined it would be done over the telephone. Now complications began to arise. It turns out that Griffin would not call us, we had to call him, and our primitive technology would not allow us to do that. Griffin was adamant about not making a call. I pressed him on the subject, and he said it was his policy never to make the call. I found this notion of a policy without an underlying principle somewhat intriguing, but Griffin replied that it was a question he felt no need to answer. Well, we wrangled for several months trying to find an acceptable format, and then I mentioned to Griffin in an email that Ryan MACKEY had written a 200-page paper critiquing Griffin's chapter on the NIST report. Griffin asked MACKEY for a copy of the paper, and MACKEY sent him one. Griffin then disappeared. He went to Europe on a lecture series. I asked him when he would be ready to do the show. He replied that he'll get back to me when he returns to this country. Someone on the James Randi forum then posted an announcement by Griffin that he was prepared to debate any of the prominent debunkers. I wrote to Griffin and I said, "This is wonderful news. Now you are willing to appear on Hardfire and face either Mark Roberts or Ryan MACKEY." Griffin announced that no, he had decided he would not appear on Hardfire because he had discovered somehow that I was dishonest. I wrote him back and I said, in effect, well, I assume we won't be seeing any examples of my dishonesty. And that put paid to the idea of having David Griffin on the show. Now, Ryan MACKEY is the man who wrote the paper that drove David Griffin into hiding. You can find MACKEY's paper on the net. We will show you a link. But I'd like to ask Ryan, when you undertook this project of critiquing MACKEY's chapter on the NIST report, did you experience the sensation that I experienced? I felt that I was walking through a cloud of locusts with my mouth open. The sheer density of error was staggering. You couldn't read a sentence without encountering a misstatement of fact, an error, an outright falsehood. Am I being too harsh?
Hi, Ron. It's good to be back. You know, it was a very interesting experience. The paper that I originally wrote has been out for over a year now, and since then I've added some more chapters to it. I've added a summary of some of the legitimate science that has come out since then and how that conflicts with what Griffin stated. I've also taken on the very few responses to my paper, none from Dr. Griffin himself. But I was really surprised. The paper turned out to be quite a bit larger than I expected, because I could not find a single major claim that, in my opinion, is correct. And I've asked other members of the truth movement to come up with one. And what's interesting to me is that since the paper came out, the response to it has been very, very light from the truth movement. Most people I talk to about it come out with the answer that David Griffin is wrong, or he works for the government himself, and this is all fantastic to me. Obviously, I don't think he's working for the government.
Did you say you found something like 180 errors in 54 pages?
Yeah, it would be difficult to count all of them, but I was responding to approximately a 50-page chapter. I limited it to that because this was on his understanding of the NIST report. The NIST report is freely available, so it's very easy to verify if he's got it right or not. And I found myself writing 180 pages just to correct those misconceptions. But those are his opinions, those are mine. I encourage people to read them and see what you think. See which one of us you think is telling the truth.
And, of course, Griffin is welcome to respond here, as are any of his defenders. I can predict with complete confidence that they will not take up the challenge. Without further ado, I'd like you to return to where we left off in the last show.
Okay, so where we were last time, we were looking at page 1-12. Let me briefly recap what we did. We're looking at the question of what happens when an aircraft crashes into a steel frame structure. Does it have the energy, does it have the force, does it have whatever it takes to damage the steel, which is admittedly stronger and harder and quite a bit heavier than the aircraft itself. Now what we did is we walked through a couple of simple equations, put together a very simple model of the situation, looking at what happens when the fuel, for instance, contained in the aircraft wings, crashes into the perimeter columns. And we came up with a fairly simple calculation. So what we do next is we look at the numbers we calculated and we compare them to the behavior of a steel column. Now this is a little bit more complicated. What you're looking at on page 1-12 there is a graph taken from the NIST report. This is what's called a pressure impulse curve. You've got pressure on the vertical axis, you've got impulse on the horizontal axis. And those lines you see, those describe the regions of either survival or breakage of the column. If you're above and outside those lines, then that means you've got too much pressure, too much impulse, the column will break. If you're down below those, it means you either don't have enough pressure or you don't have enough impulse, and the column is likely to survive. Now the numbers we just computed for the two different cases, World Trade Center 1 and World Trade Center 2, they're different because the aircraft were moving at different speeds. Those are listed there by those red X's I put there. Now the dots on there are the calculations that NIST themselves put together. This can all be found in Chapter 10 of NC Star 1-2B. And what you see is, even though our model is extremely simple, our values are pretty close to the ones they came up with. They're a little bit more impulse than what they saw, but they're in family. And for a simple model, that's close enough. Now the other thing that you get from this graph is what we computed is way outside the survival range. Now something else I need to point out, these lines are drawn here for a core column. These are not drawn for a perimeter column. These are for the core columns, which are much stronger, much thicker. So what this means is our model predicts that yes, indeed, those impacts will definitely destroy perimeter columns on contact. And that's what the numbers say.
So in other words, the effect that we observed, that the plane simply sliced through the building, is really the only thing we could expect to see. It can't do otherwise.
Right, that is what the model predicts. Now you can even go a little bit farther, and we're going to do that soon. You can start looking at this curve to say, what would it take to get the opposite result? How low should the pressure be? How low should the impulse be in order to get that opposite result? And ask yourself how likely it is for that to happen in what we witnessed that day. So let's go ahead to that. Let's go to page 1-13. This is a brief summary of our findings so far. What we find when we compare our model to what this other model says is our numbers are about the same. Our impulse is a little bit high, but that's okay. I'm guessing that the reason that our impulse is higher than theirs is their model is more complicated. They probably simulate better fluid dynamics than we did, and that probably sheds some of the fluid column to the side. So there is a detail. You always have to make sure you haven't simplified so much your answers are totally wrong. But in this case, our simplification is pretty close. So let's go ahead to page 1-14.
I just want to call attention to the conclusion that the fuel alone was sufficient to sever the core columns.
Right.
In other words, we're not talking about the additional weight of the aircraft itself.
That's right. Now, there is a fine point, though. In the actual structure, the fuel did not contact the core columns until after it already hit the perimeter column. So it's unlikely that in the case of the World Trade Center, the fuel would have on its own destroyed the core columns. But what this means is if you had a much stronger column at the perimeter on contact, it would have been destroyed. So that's what this result means. And this is gone over in much more detail in NC Star 1-2B, which again is freely available if anybody wants to read through it. It's an interesting document. So let's go ahead to 1-14. So before I was suggesting we could also look at that curve to see what it takes to get the opposite result. And let's now do that. If we look at that curve, if we look at the numbers on it, we come up with a guess that a pressure below about 800 psi will result in a column surviving. That's our threshold. Remember, in our case, we're well above that. We're in the 4,000 to 6,000 range. Now, the equation we worked out in our simple model for pressure is pretty simple. The pressure is equal to the fuel density times the velocity squared. We know the fuel density. You can go look it up. So if you work through the numbers, you come up with a velocity to get this pressure of about 270 feet per second. So what this means is our model that we worked out predicts if you're going over 270 feet per second, you are going to break columns. If you're going under 270 feet per second, you're probably not going to break columns. And that works out to a speed of about 185 miles per hour. So if you go back and look at the cases of aircraft that didn't do much damage and aircraft that did, what you find, interestingly enough, the aircraft that didn't do much damage are all low speed. They're either landing, they've just taken off, they're civil aircraft, and this number is actually pretty plausible. But having said that, in the World Trade Center events, the aircraft were going so much faster than this that, again, it makes perfect sense at the level of resolution of this discussion to do that kind of damage. So this is the other reason you do a model. It not only gives you a way to understand what happened, it gives you a way to predict what can happen in the future. And that's really the core of science. So let's go ahead to 1-15. Something else you should always do is think about whether these results really make sense. You should just stop and do what we call an idiot check sometimes. Does the pressure we computed really make sense? We're talking the 4,000 to 6,000 range, and we're saying that's enough to cut steel. Well, you can think about a water jet cutter, for instance. Some of them flow at about 900 miles per hour, and they can cut through many, many inches of high-quality steel. So, yeah, that makes sense. What about the impulse? Like I said, impulse is not a quantity you run into every day, so it's going to be a little bit unusual. But the impulse we worked out, again, is roughly equal to what a car on the freeway has in terms of its total momentum. So think about a luxury car at freeway speed hitting a steel column, and think about if it's possible for it to break that column off completely. And, of course, the answer is yes, that is reasonable. The other way to do an idiot test, we already did, is you look at what other people are doing. You look at their results. And we took a look at the NIST model in Chapter 10 of 1-2B, and we found that, yeah, our results are pretty consistent. It's not identical, but that's what we expect for doing a simplification. So with that, we're ready to wrap up. What we conclude from this exercise, and this is on page 1-16, we conclude that the momentum from the fuel alone is enough to destroy the steel columns. Now this explains a lot of things. This explains why the low-speed crashes do so little damage, why the high-speed crashes do so much damage. It also explains, if you get into more detail, if you look at the records and the reports of the event, the aircraft did not completely create a cutout of themselves when they hit the structures. The wing tips did not penetrate. And NIST explains how the region between penetration and not penetration is where they think the fuel level in the wings was at that particular time. The lighter structures are probably not going to do as much damage. They'll still break glass and create another problem. But again, this is exactly what we expect to see. What we learn from this is that it really is mass and momentum. It's not strength and hardness that make all the difference. Obviously, you could make a structure strong enough to resist this, but it would take columns that are far, far stronger. And there really is no compelling reason to do that unless you expect to be hit by an airplane. So what we conclude at the end of this exercise is the damage we see is completely credible. And that is good enough to dismiss the truth movement when they say this damage doesn't make sense. We turn around and say we've gone through this exercise. To us, it does make sense. So if you want to demonstrate that your claim is correct, the burden of proof is now upon you. You need to improve your reasoning. You need to show where we've made a mistake. You need to show where one of our assumptions is either wrong or grossly distorting the result. And until you do that, this is the right way to look at the problem. So there you go.
Now, this concept of the idiot check, this would explain why there is no real controversy in the scientific community over the events of 9/11. I mean, there are countries that are certainly unfriendly to the United States, but you will not find any of their physicists or engineers saying, wait a moment, this is wrong, the aircraft would have bounced off the building. No one is saying that, no one who is a serious scientist.
Yeah, that's right. There is a little bit of discussion still in the scientific community, but they're all over the details. I'm not aware of any serious scientist, I'm not aware of any legitimate publication where any scientist has suggested that what caused the structures to collapse was anything other than the aircraft impact, the resulting fires, the interaction with the structure as built. The discussions that are still going on have to do with how vulnerable the structures were to fire, and whether that was a flaw of the construction, whether the design was perhaps not quite as robust as it should have been, or whether there really was no hope for them anyway, even if they had been built to code. So there are still some discussions, but there's absolutely no scientific disagreement that would help the truth movement. All of these discussions, every legitimate paper that's ever been put out and properly reviewed, supports these positions. There's been quite a few of them from many countries, from government, from non-government, from companies, from individuals, and they all basically add detail to the story, but they don't change it.
One distinction that I wanted you to make for our audience, you spoke about strength and hardness. Now, it's my understanding from what you've said that a softer substance could be stronger than a harder substance.
Yeah, that's right. You can think about, for instance, glass is a very hard substance, but is not necessarily strong. It fractures easily. You can have a lot of things that are very hard but very brittle. They don't flex very much before they start coming apart and start shedding their mass in a collision. It really is fairly complicated, and part of the difficulty is because hardness is a difficult thing for us to describe. It doesn't have a regular unit. We usually think of hardness either things like the regular geological scale that goes from 1 to 10, where diamond is a 10 and talcum is a 1.
Is that the Mohs scale?
Yeah, that's the one. Another example would be when engineers talk about hardness, what we do is set up a test, like a Rockwell hardness test. What that basically is, you set up a device that's repeatable, and it makes a little dimple in the material, and then you hit it with a known force and see how much the dimple expands. But these things are complicated. They don't translate well into this kind of discussion.
The Holocaust-denying Bishop Richard Williamson, it turns out, is a 9/11 truther. Surprise. He argued that the soft nose cone of a Boeing 757 couldn't possibly have caused so much damage at the Pentagon. Now, I think he's missing the point entirely about momentum, impulse, the forces generated by the collision. But how could you try to change the mind of someone like that?
Well, the obvious answer is sure, the soft nose cone, which is probably fiberglass, probably didn't do that much damage, but there's 100 tons of aircraft behind it, moving several hundred miles per hour. It really doesn't make that much difference. You can't simplify it like that. You need to think about the total amount of impulse that's being applied to that structure, which is huge. And you need to think about the capacity of the structure to resist it. In the case of the Pentagon, you're dealing with a different structure. You've got concrete with a lot of rebar, a lot of mass to it. And this is part of the reason why the Pentagon fared a little bit better than the World Trade Center did. And there's various other reasons. But if you want, you can walk through the calculations, and they will leave very little doubt that there's plenty of energy there, plenty of momentum there to get it done, no matter what the aircraft was made of. Even if it was a water balloon at that speed, it would do enormous damage on impact.
I know you have a lot to say about the collapses of the towers. I wanted to put one issue to rest. We can deal with it briefly because it seems to be of interest only to the Dottie no-planers. They keep talking about the speed of Flight 175, which has been estimated at roughly 540 miles an hour. There's a fellow named Jeff Hill who calls every aeronautical engineer he can find, and he tries to somehow trick the guy into saying that a Boeing 767 can't go that fast. He always omits a tiny detail. He neglects to tell them that the plane he's referring to came out of a 20,000-foot power dive. Is there any controversy here? Is there any aeronautical engineer anywhere who doubts that this plane was going 540 miles an hour?
Well, there's a lot of aeronautical engineers in the world, and there's probably one or two that believe, some fairly unusual things. But the simple fact is that it's happened before. The example I use is the one of Egypt Air 990, which was, we think, deliberately dived into the ocean at a great speed. It was the same aircraft, practically. It was also a Boeing 767.
And that was going faster than 540 miles.
That's right. It got up to about 650 miles per hour. So there really is very little doubt. If you dive an aircraft steeply enough, you can overspeed it. If you have a rookie pilot at the helm of a jet plane and he's not paying attention, he dives too fast, he can get himself into trouble. So the thing to keep in mind is the speeds we're talking about here are probably a lot higher than a Boeing could go if it was going just flat and level. At those, at those speeds and that altitude, the drag would probably not let it go that fast, or it would suffer some skin damage. But if you're diving, your effective power goes up so much, and you're only pulling out of the dive for a couple of seconds. There just isn't time for drag to slow you down to that speed.
What about the possibility of damaging the plane in the dive? In other words, would the pilot have damaged the plane by diving 20,000 feet so quickly? I mean, we have the air traffic controller, Dave Batiglia, talking how stunned his colleagues were by the descent of this plane. They were literally ticking off the feet per seconds that the plane was how fast could you dive without destroying the plane?
Well, there is definitely a possibility they did damage the plane during the dive. We'll never know that for sure.
I mean, of course, they didn't care.
That's right. You have to understand you are dealing with a terrorist who is not the world's best pilot, doesn't really care. All he needs is for the jet to hold together a few more seconds and he's done. But there are also examples of aircraft that have sustained much greater speeds and have made it back. One of the best examples, there was a China Airlines 747 some years ago that had a problem with an engine flame out, and the autopilot didn't work the way the pilots thought. They actually broke the sound barrier in that aircraft, and there was damage to the airplane, but it was able to land safely. So there is every reason to believe that these aircraft were capable of absorbing that kind of punishment. If I had been the pilot, I can't imagine why I would do anything so awful. But I would say doing that maneuver was probably a little risky. They probably should not have done it. But there's absolutely nothing unreasonable about them coming through it okay. This is just not that big of a risk.
As you know, John Lear, the son of the inventor of the Learjet, believes that parasite drag would prevent the Boeing 767 from attaining a speed of over 500 miles an hour. Now, Lear also believes that the moon is colonized by space aliens, but let's deal with this notion of parasite drag. What is he talking about?
Sure. What he's talking about is just regular aerodynamic drag. And we call it parasite drag because it robs power. So if you took a Boeing aircraft under controlled test and you dived it from some high altitude to get up to the speed and leveled off at low level, near sea level, then over time it probably would slow below 500 miles per hour. I don't know exactly what the performance limits on the engines and the inlets and drag works out to be, but it's going to take some time. When you come out of that dive, you're going to be going very quickly, and drag is a force. Force leads to acceleration. Force does not immediately set the velocity you're going. Again, this is Newton's second law in action.
And this is once again another instance of the conspiracy theorists misrepresenting what Newton said. I know when we get to the subject of Anders Bjorkman, you're going to have a lot to say about how Newton gets twisted out of recognition, but we'll have to save that for the next show. So for the moment, we can conclude that there is, from a physical standpoint, nothing unusual about a plane coming out of a steep power dive attaining the kind of speed that it would not otherwise be able to attain at sea level.
That's perfectly ordinary, and you can test it yourself. Take your bicycle, measure how fast you can pedal, and that is going to be a drag-limited effect. You reach equilibrium when the drag and the friction and everything is as hard as you can pump. Then take your bicycle to the top of a steep hill, and once it levels out, see if you immediately go back to that speed or not. It's a very simple concept.
It's remarkable that none of these people would ever think of actually subjecting these notions to a test.
Right, and that's part of the reason we know that this isn't actually science. Because science demands review, and it demands revision, it demands repeatability. And if you don't submit your calculations, you don't make your assumptions clear, you don't publish in a venue that other people can understand it, you're really not participating in the process. Now, some people do that. There have been a very few examples of folks in the truth movement who do put out these kind of calculations. And I actually have more respect for them. The problem is all the ones that we've looked at turn out to have fairly glaring problems.
And on that note, we're going to break off for tonight. We'll come back next week for the final installment of this discussion of the physics of 9/11. We thank Ryan Mackey for his fascinating lecture. We will have some questions for him. Thank you for joining us. We hope to see you again on Hardfire. Good night.
Thank you.
This work is copyright 2008 by Ryan Mackey. All rights reserved. All opinions are those of the author alone and do not represent any agency, public or private. Photographs are used in accordance with fair use guidelines and may be subject to their own copyright protection. The author can be contacted at rmackey_email@earthlink.net. Additional online resources: 9/11 Myths, www.911myths.com. Mark Roberts Collection, WTC7lies.googlepages.com. 9/11 Guide, 911guide.googlepages.com. Hardfire is funded in part by the Libertarian Party of New York. www.ny.lp.org